Good day, Doctor. I'm Chong Kai-shin, and I am going to make an introduction about Joule-Thomson effect. In thermodynamics, the Joule-Thomson effect describes the temperature change of a real gas or liquid when it is forced through a valve or porous plug while keeping it insulated so that there is no heat exchange with the environment. This procedure is called a throttling process or Joule-Thomson process. The gas cooling throttling process is commonly exploited in refrigeration processes such as air conditioners, heat pumps, and liquefiers. In hydraulics, the warming effect from Joule-Thomson throttling can be used to find internally leaking valves, as this will produce heat which can be detected by thermocouple or thermal imaging camera. Throttling is a fundamentally irreversible process. The throttling due to the flow resistance in supply lines, heat exchangers, regenerators, and other components of machines is a source of losses that limits the performance.
My name is XIAN, and I'm going to introduce the Joule-Thomson effect. In thermodynamics, Joule-Thomson effect describes the temperature change of real gas when it undergoes expansion from high pressure region to lower pressure region without the transfer of heat. This effect is discovered by James Prescott Joule and William Thomson in 1852. Let me explain further about this effect by a simple diagram. This is an adiabatic expansion where the gas initially at P1, V1, and T1. Then, the gas will expand continuously to the other side through the small opening. The container is insulated well to ensure no heat is lost to the surrounding, therefore Q equal to 0. When we push the gas using the piston with an external pressure of P1, the gas is forced to expand into the second container at P2, which is lower than P1. Then, we can observe that the temperature of the gas decreases after the adiabatic expansion due to the intermolecular attraction. Hence, the adiabatic expansion of real gas causes the increase in potential energy associated with the decrease in kinetic energy, while keeping the heat energy constant. Besides, we can also determine the change in internal energy by knowing the work done on the system, since delta U equals to W.
Hi doctor, my name is DINIE. So, during such an expansion, there would be no change in enthalpy. Furthermore, the determination of whether the internal energy increases or decreases takes place by whether work is done by the liquid or on the fluid. This means that it is determined by the initial and final states of the fluid's properties. The Joule-Thomson coefficient makes possible the quantification of the temperature change during a Joule-Thomson expansion display. Furthermore, this coefficient may be either positive or negative. The coefficient turns out to be negative at extremely high and extremely low temperatures. Furthermore, it is negative at very high pressure at all temperatures. Moreover, being positive corresponds to cooling, while being negative corresponds to heating. So the Joule-Thomson effect formula is as below.
My name is Afrina. I will explain the first part of the industrial application of Joule-Thomson effect. The industrial application of the Joule-Thomson effect in the vapor compression refrigeration cycle uses its cooling potential by involving the rapid expansion of a real gas across a valve, which helps to cool down the gas. The cycle involves four components, which are compressor, condenser, expansion valve, which known as jetty valve, and evaporator. Firstly, the refrigerants such as CFC or R717, which are in a gaseous state, enter the compressor at a low temperature and low pressure. So, a positive displacement compressor is used to increase the pressure and the temperature of the refrigerants. Then, the superheated refrigerant is desuperheated and condensed to a liquid using a condenser.
Next, the refrigerant is rotated through the Joule-Thomson valve. When the refrigerant enters the Joule-Thomson valve, it expands and releases pressure, which results in the reduction of the temperature. And as you can see in this diagram, the pressure P1 and the temperature T1 of the refrigerants at the axis of the condenser is reduced to a lower pressure P2 and temperature T2 in the evaporator. In this step, the system is adiabatic system, which means Q equal to 0, and the change in enthalpy also equal to 0. Lastly, when the cool refrigerant gas is used to cool down other fluids, such as air and water, the refrigerant itself gets heated. Hence, it is then sent back to the compressor in the step 1. Hence, this is show how the refrigeration system continues.
In conclusion, Joule-Thomson effect can be concluded as the change in temperature that accompanies expansion of a gas without production of work or transfer of heat. Applications of Joule-Thomson effect generally use the cooling potential rather than heating, as there are more convenient ways to heat a process. Some applications where the cooling of expanding gases are: first, refrigeration; second, gas separations; third, air conditioning; and the last one is liquid gas production. For this assignment, we choose industrial application in vapor compression refrigeration cycle, which involve 4 components. First, compressor; second, condenser; third, expansion valve, which is known as jetty valve; and fourth is evaporator. Hence, the change in temperature of a gas as it experiences a rapid change in pressure from passing through a valve, orifice, or nozzle may represent a safety hazard or an opportunity depending on the process.